is Maria Aparicio.
And I'm Don Hettman, and we're presenting our project for ECON 463, Winter 2020, on hydrogen fuel efficiency for the future.
Mm-hmm.
So here's an overview of kind of what we'll be talking about. We're going to start with an introduction and our research question, and then we're going to talk about fuel cells and what is hydrogen fuel, just to give you a basic understanding of what we're talking about, because some of it's kind of specific. And then we're going to talk about the hydrogen body structure of a specific fuel cell and sort of battery flow in vehicles, delayed delivery of battery, a battery flow chart, how we save energy, and some more specifics on fuel cells and a fuel cell car. And then we're going to talk about practical stuff like a map of where hydrogen fuel fill-up stations exist, and some economic prospects and issues and solutions. Alright, so our research question was, is hydrogen fuel efficient for the US economy, and will it be efficient for future transportation? We're looking specifically at cars, but yeah, that's our question. So, just for those of you who don't know what a fuel cell is, it's basically just a battery that doesn't need to be recharged. It takes input of a fuel and puts out electricity. So, the protons and electrons of a fuel, such as hydrogen, are separated, and the electrons are moved around really fast and they create electricity, while the protons end up as waste. And it can produce electricity and heat as long as fuel is put in, and they are used in cars, to power portable electric devices, on NASA missions, and as stationary electricity generators. So pretty versatile tool. Hydrogen fuel is one of the fuels that can be put into a fuel cell, and hydrogen is the most abundant element in the universe, but it's pretty difficult to find it by itself. It's most common in water, which is just 2 hydrogens and 1 oxygen. And you can separate it to just hydrogens and oxygens through electrolysis, which is a process, where you pass electricity through water to separate those 2 elements. And then you can just use hydrogen and separate it further into protons and electrons. This can also be achieved from chemical processes, from hydrocarbons or the hydrogen carriers. And once you get hydrogen fuel, it's pretty clean and renewable. It's just a conversion of heat to power, and it converts chemical potential energy directly to electrical energy, unlike an internal combustion engine or an electric car. And yeah, once you go through electrolysis, you get just hydrogen fuel, which is then put into a fuel cell, like I said before, and then the proton and electron are separated. So yeah.
Alright, so we're going to talk about the basic battery structure for the fuel cell, and we got this picture from Cummins Inc. So basically, the basic structure of the fuel cell, it consists of a negative and a positive. So here the negative is the anode, and then the positive is a cathode. So basically, if we were to supply this fuel cell with hydrogen water, so basically the anode would take the water, and then from over here you would take the oxygen, and the cathode would convert it into energy. And so in the middle, between the anode and the cathode, is the PEM, so basically it's the proton exchange membrane. So basically that is, it's a cell that uses hydrogen gas H2 and oxygen gas O2 as fuel. To the next slide. Alright, so I'm going to introduce you guys to keywords of what I'm talking about, because I'm going to introduce you into like battery energy and saving energy. So FC is fuel cell, and BAT is supercapacitors, SC is excavators, SOC, BAT means the state of charge of a supercapacitor, and P parenthesis rec means the power requirement. So this is a basic introduction of how the battery flowchart works. You can just take a look at it, and I'll explain it on the next slide, like what each, so like how the power requirement works and how the state of charge works for the supercapacitors. So go to the next one. So basically that chart that you saw was a representation of decreasing fuel consumption in the fuel cell by integrating BAT and SC into the system. Now, if the state of charging, based on this, if the state of charging of the supercapacitor is greater than the state of charge of the supercapacitor of the minimum, so right here, then the fuel cell and the supercapacitor make the vehicle drive. And over here, if you see the regeneration mode, so basically if the power requirement, if the state of charge of the supercapacitor is smaller than its lower limit state of charge of supercapacitor at minimum, the supercapacitor will be charged. So if excavators are charged only if the state of capacitor or the state of the excavator is smaller than the state of the charge, then the excavator, pardon. So if the state of charge of the excavator is smaller than the state of charge of the excavator at minimum, it means that the power demand exceeds the max power of the fuel cell and the capacitor is combined. To the next slide. So basically the delayed delivery of the battery, so this is like the negative side of that, of if you don't reach the limits of the battery. So if in the SOC BAT, so the state of charge of the supercapacitor is lower than the limit state of charge of the supercapacitor at minimum, that means that the fuel cell has to charge the supercapacitor first, then that delays the power delivery process. Now, if the state of charge the fuel cell is lower than the state of charge fuel cell at the minimum, it means that the supercapacitor is charged, but the fuel cell does not have enough power to satisfy the demand power. So basically, the supercapacitor is at discharge mode, and that means that the fuel cell has to charge the supercapacitor. And this leads to like an unstable system that decreases the lifetime of the device. And so this is another chart that shows the saving energy. And this has like a lot of, so if the power requirement is negative and if the power requirement is positive, so you can go into the next slide and I'll explain. So basically, if the power requirement is negative, the vehicle will be in regeneration mode, and so the fuel cell is charged first, and if the state of charge of the fuel cell is low, then erase that. Just know that if it's negative, the car goes in regeneration mode. And so the BAT is charged first. And then if the power requirements are positive, the fuel cell can satisfy the power demand, and this provides energy for the vehicle. And so if the power demand exceeds the power of the fuel cell, the fuel cell delivers its maximum power, and so the fuel cell delivers the remaining power. So yeah. And then here, what I was trying to explain from the saving energy, if you were to combine the fuel cell with the supercapacitor and the excavator, you get this levels of energy. So basically, if you were to combine the fuel cell with battery and the supercapacitor, you get a very high power. And then if you were to just have a fuel cell, you would just have a low power.
So there's definitely room for building off of hydrogen technology, and you know, it's not just hydrogen fuel cells, it's so much more than that.
Yeah, definitely.
Alright, so we looked specifically at Cummins Inc. That's where we got a lot of our information from. They're a corporation that's been around since 1919, and they sort of lead the charge on hydrogen fuel cells. Any company can contact Cummins Inc. to purchase engines, and they have pretty much two main types. They have a PEM, like how we looked at earlier, which was the protein exchange membrane kind of fuel cell, which uses hydrogen fuel and oxygen from the air to produce electricity. Or they have the solid oxide fuel cells, SOFC, which are pretty fuel flexible and we didn't really look at because they use carbon monoxide as a fuel and not hydrogen, which isn't nearly as clean. And yeah.
I would like to add on, for the PEM, that's what we are looking at more, so it's based on vehicles.
This is an example of a car that runs off of hydrogen fuel. It was called the Honda Clarity. It has a 174 horsepower engine, a driving range of 466 miles, and it takes 3 minutes to fill up the hydrogen tank, which is pretty much like any other car, if not a little bit more. And when combined with a power exporter, it can power a house for 7 days, so that's how powerful it is. I think it was put on the market in 2018, I believe, but it's not on the market anymore because not enough cars were sold. But it's still an example of how this is possible, just not quite yet. It's kind of in the distant future. Even though it's in kind of the distant future, this is a map of the hydrogen stations that currently exist. They're all in California, and there's 40 total, or 40 that are open. The green ones are the ones that are open, and the yellow are in development. And you know, some of these are checked off, and some of them are checked on, and I just picked the ones that are the most relevant and have the most stations. So as you can see, they're pretty much in LA and San Francisco, and they're all in California. And so I zoomed in over on this map to just the Los Angeles area to sort of show you how many of each kind of station there are. So the yellow ones are the ones that are in development, and the green ones are the ones that are open. And these blue ones, the light blue and the dark blue, are for buses and trucks, which is another avenue of hydrogen fuel technology. Cummins Inc. actually sort of came out with a hydrogen fuel powered semi-truck in 2019, I believe it was. And so that was pretty cool. It's definitely an avenue for long distance trucking. And as far as economy prospects go, research shows that by 2030, hydrogen fuel technology could generate $140 billion in revenue and support 700,000 jobs. And by 2050, $750 billion in revenue and generate 3.4 million jobs. And this information is shown here. Hydrogen in the US could strengthen the economy, create a very competitive source of domestically produced low-emission energy. That's the main thing about hydrogen fuel, is that it doesn't produce any CO2, which is very good for climate change. And so yeah, we just looked at these little numbers over here, not really so much of these, but 2030 and 2050, it's looking pretty good. And some more about the prospects of the economy. On the next slide, there's a little bit of a chart, but I'm just going to explain it beforehand. All the measurements are in parts per million, and the hydrogen demand potential across all of these applications could reach 17 million metric tons by 2030 and 63 million metric tons by 2050. And so here's that chart. 2015 is the base, just sort of where they got their information from, and then this one is 2030 and this one is 2050. And each of the columns on the left are sort of the more conservative estimates, and then the ones on the right are very ambitious. So as you can see here, it's sort of split up into a bunch of different categories, but most of it is existing feedstock. And so this is the hydrogen's energy demand as projected.
Right, so we're going to talk about the hydrogen issues and solutions. So for battery, there's an issue about going thermal stability. And one of the things that was mentioned, and it's cited here on the side for you guys to look at, one of the strategies that they were saying is using solvent-free ionic liquids for electrolytes, and development of new safe materials would be a mitigation strategy for thermal stability. As well as for supercapacitors, they were saying the safety concerns were thermal stability, but they also recommended as a mitigation strategy using solvent-free ionic liquid electrolytes. And hydrogen storage, the safety concerns were temperature rising during refueling, and so one of the mitigation strategies would be high initial pressure, a low ambient temperature would help out. Also pumped hydrogen power, one of the safety concerns was dynamic effects due to normal and transient operation, and based on the mitigation strategies, we were considering like the hydrodynamic issues in the design process.
Yeah, so in conclusion, going back to our research question, is hydrogen fuel efficient for the U.S. economy? And will it be efficient for future transportation? As far as the economy goes, it would be a very good idea. As we showed earlier in those little numbers, it could really make a lot of jobs and make a lot of money for the United States. That is pretty far projected though. It's not anywhere in the near future.
Yeah, and also based on like the battery analysis, it seems like it's simple, but there's a lot of, the state of charge using capacitors, like adding capacitors, supercapacitors, and what was the other one? Supercapacitors and the fuel cell. Yeah, like if you add those two to create the hydrogen power, you can see the levels of energy between those. So I think it's just exploring more of the battery structure. We would be able to have efficient prospects of the economy for the hydrogen.
Yeah. And as far as the amount of cars in use right now, there aren't that many, and like I said before, the Honda Clarity is not on the market right now, but that definitely sort of comes after the more production of hydrogen fuel cells themselves, and just sort of more production of hydrogen pumps and all that stuff sort of comes before the amount of cars in use. And definitely another issue is the limited location of hydrogen pumps. I mean, they're all in California, and not everybody lives in California, even though a lot of people do. So that would definitely be something that needs to be accomplished before hydrogen fuel cells could be a normalized thing. But as we mentioned before, it's efficient for the economy, and maybe in the future this would be a great transportation option.
Mm-hmm.
It's clean, it's renewable, it's very easy to obtain, and yeah, no CO2 emissions. Pretty tantalizing option. And this is our
We're excited.
We're excited.
Thank you for watching.